In this program, we will see how humans adapt to very high altitudes. We will learn how to climb the steepest mountainsides and find out how to harness avalanches. The destiny of humankind is inseparable from the existence of the mountains. Our ancestors believed them to be supernatural. For the ancient Greeks, for instance, Mount Olympus was home to the gods. For we humans, mountains are not very hospitable places. At high altitudes, they can be downright hostile. A high mountain is one of the most inhospitable places on Earth. The cold, the wind, and isolation severely limit the possibilities of human survival. Also, the higher the elevation, the lower the atmospheric pressure and oxygen level. At an altitude of 5,500 meters, there is half as much oxygen than at sea level. And atop Mount Everest, 8,848 meters above sea level, there is 4 times less. That shortage of oxygen, called hypoxia, poses a real threat to human survival. And yet, one can become acclimatized to it. When you go up in altitude, the organism initially adapts to the lack of oxygen by quickening its heartbeat and breathing rate. This increases the amount of oxygen reaching the body cells. During breathing, oxygen is taken up by the lung alveoli. The oxygen molecules go through the walls of the tiny sacs and fix on the hemoglobin, a molecule carried in the red blood cells. By breathing more rapidly, more molecules of oxygen reach the lung alveoli and enter into the bloodstream. Also, when the heartbeat quickens, a greater number of red cells come into contact with oxygen molecules and pick them up. At an altitude of 2,000 meters, these two mechanisms ensure a better distribution of oxygen throughout the body. They are, however, only effective at rest and insufficient for strenuous exertion when the body requires a greater amount of oxygen. That's why beyond 3,000 meters, a person's physical strength is rapidly sapped away. However, after a few days at high altitude, the organism goes into a phase of acclimatization. A hormone produced by the kidneys causes the number of red cells in the blood to increase. This process is one of the keys to adapting to high altitudes. It enables the blood to ferry more oxygen to the body tissues, thereby helping mountaineers to regain some of their strength. This is why it is imperative that alpinists always spend several weeks at what is called a base camp before undertaking the ascent proper. But for some climbers, the dream can turn into a nightmare. A substantial percentage of people are prone to mountain sickness. The symptoms include nausea and violent headaches and can sometimes lead to edema, that is an excessive accumulation of fluid in the body tissues. In cases of pulmonary edema, fluid enters the alveoli, preventing the oxygen from circulating freely in the bloodstream. The victim may then die of asphyxia. Cerebral edema can cause severe brain lesions. Until recently, the only cure for edema was to return to a lower altitude. But this cannot always be done in time to cure the problem. Specialists have now designed a portable recompression chamber in which the patient is placed. Using a pump, the pressure in the chamber is increased, simulating a decrease in altitude of up to 2,300 meters. 30 to 60 minutes in the chamber will cause part or all of the symptoms to recede. Researchers have also developed screening tests to detect people at risk. The subject pedals a bicycle ergometer while breathing a gaseous mixture low in oxygen. simulating a high-altitude situation. By measuring the person's heartbeat, the amount of air breathed, and the oxygen content of his blood, the doctor is able to assess his susceptibility to mountain sickness before the expedition starts. Conditions at high altitudes can be simulated even more realistically in a hypobaric chamber, where the atmospheric pressure can gradually be lowered until it reaches that found at the summit of Everest. Temperatures can also be lowered to minus 40 degrees Celsius, while fans generate violent winds. This simulation enables the experts to check a climber's resistance to intense cold and to very high altitudes. Besides helping to identify climbers likely to contract mountain sickness, hypobaric chambers are used to hasten the acclimatization process of expedition members. For instance, a group of mountaineers was able to assault Mount Everest after spending only 6 days at the summit of Mont Blanc, then 4 more in a hypobaric chamber at a simulated altitude of 5,000 to 8,500 meters. Normally, they would have had to spend several weeks at a base camp before attempting their climb. We have to wonder why it is that man has the ability to adapt to such altitudes. Scientists believe the answer lies with the human fetus. In its mother's womb, the fetus actually lives in a state of hypoxia, as if it were at an altitude of 7,000 to 8,000 meters. Thanks to adaptation mechanisms as yet little known, fetuses are able to easily survive such low concentrations of oxygen. Perhaps it is by calling on these atavistic mechanisms that climbers are able to reach the summits of the highest mountains in the world. Scientists' interest in mountains goes back a long way. The first ascensions were made to explore and map them. Then adventure and challenge gave birth to a new sport, mountain climbing. Formerly considered a simple ascent technique, rock climbing, or free climbing, has become a sport in its own right. Owing to more sophisticated methods and training, today's climbers are pushing back the limits of the insurmountable. Although climbing is also practiced on ice walls and hardened snow slopes, rock climbing is the most popular form of mountaineering. It can be practiced on natural walls or up an artificial wall embedded with hollows and bumps, and is as exhilarating an experience as climbing the steepest cliff. Rock climbing requires as many mental skills as physical ones. Concentration, a keen sense of observation, and body awareness are just as important as physical fitness, flexibility, and strength. One of a climber's essential skills is mastering balance. It involves controlling the position of one's center of gravity. That point, where all the forces exerted on the body counterbalance each other, is normally located a few centimeters behind the navel. To maintain his balance, a walking person must keep that point above the surface delimited by the parts of his feet that are in contact with the ground. That surface is a quadrilateral or four-sided geometric shape. Should he fail to respect the rule, the walker will lose his balance. Beginners ascending a sloped wall must also keep their center of gravity directly above the area their feet are in contact with. To help beginners comply with this principle of physics, climbing instructors recommend they keep their bodies as straight as possible, that is neither too far away nor too close to the wall. More advanced climbers will often depart from this rule, though, for instance, when they face a vertical wall. This requires a considerable amount of body awareness. Also, center of gravity rule no longer applies when a climber is dangling from an overhang, a wall at an angle of more than 90 degrees. Ironically, it is easier to ascend an overhang than a vertical wall because the climber is in a better position to see the wall. Rock climbing also depends on another physical phenomenon: friction. Even on level ground, walking would be difficult if there were no resistance between the feet and the ground. That resistance is the result of the roughness of the objects that are in contact with each other. In this case, the soles of the boots and the ground with its surface of minute hollows and bumps. These rough areas cling to each other, allowing the settled foot to stay put while the other foot advances. Like the walker, the climber has to make sure the friction exerted between his extremities and the rock is sufficient to keep him from slipping. The difficulty arises from the fact that the contact surface between the climber's extremities and the wall is sometimes very small, which lessens the force of friction. There are a number of techniques used to scale rock. The climber using the scrambling technique applies a major portion of the surface of his feet against the rock. This technique is facilitated by wearing climbing boots with soles of a special mixture of rubber and resin, which have a good grip on the rock. Another climbing technique is jamming, which consists of wedging a hand or a foot in a crack to get a hold on the rock. In most cases, climbers are advised to use their arms mainly to keep their balance, not to pull themselves up. Indeed, our arms are much weaker than our legs and tire much more rapidly. Also, fingers tend to become moist, which lessens their gripping power. The rule of thumb is to take advantage of as many stop points as possible so as to rest the arms. On top of requiring considerable physical skills, rock climbing involves hard mental work, similar to what might be expected of a chess player. Prior to the actual assault, the climber first works out in his mind a strategy of the moves he will make to reach his goal. Once on the wall, he has to read the rock, that is, carefully analyze the situation before him, before making his next move. To avoid working himself into an impasse, the climber also learns to predict the sequence of each of his moves several moves in advance. In rock climbing, equipment may only play a minor part in the climber's ascent, but it constitutes a crucial safety factor. So much so that the modern ropes are designed to hold a 2,500 kilogram load. Such resistance is not excessive when you consider that at the end of a 10-meter fall, a person who weighs 80 kilos exerts a real weight of 800 kilos on the rope. By making it safer than ever before, advances in technology have greatly contributed to the revival of rock climbing, without, however, detracting from the beauty of the sport and the greatness of the challenges it offers. Summer and winter, thousands of vacationers storm the mountains, usually to practice their favorite sports: skiing, climbing, hang gliding. As a rule, mountain activities are safe, but no one is completely shielded from a mountain's white rages. In winter, the apparent serenity of snow-covered mountains can be misleading. They conceal a danger for skiers and recreationists: avalanches. Avalanches are a natural phenomenon caused by the sudden breaking away of a mass of snow or unstable ice on a steep slope. In some cases, avalanches can hurtle down mountainsides at speeds of up to 200 miles an hour, tearing up thousands of tons of material and burying everything in its path: roads, chalets, human beings. It is impossible to stop an avalanche once it's begun. Its pattern is much like that of a tidal wave, or like water gushing from a ruptured dam. In the most popular ski areas where disaster could be just waiting to happen, the only alternative is to try and control them. One of the commonest methods now being used consists of routinely blasting accumulations of snow at safe distances, releasing avalanches while they are still small enough to be managed. The explosives are carried to the chosen site by cables permanently set up above a series of avalanche corridors. An explosive charge and remote detonator is attached to the cable. When it is above the chosen location, the detonator is activated, releasing the charge, which explodes. In most cases, the shock wave is powerful enough to trigger the avalanche. Naturally, care is taken to ensure that no one is in its path. In spite of these precautions, avalanches will still happen unexpectedly. These accidents usually occur due to internal changes in the snowpack. Owing to packing and wind, fluffy snow crystals, initially star-shaped, become round and compact like pellets. These changes cause the surface of the snow to harden, while the underlayer stays soft. Thus transformed, the snow forms masses so unstable that the weight of a single skier can cause them to break away. The unfortunate skier is then caught up and whisked away in the sliding mass. When this happens, rescue teams are quickly dispatched to the location. They have to act fast because the chances of finding victims alive diminish rapidly the longer they are trapped. The rescuers usually use long aluminum probes to pierce through the snow crust. Increasingly, though, skiers have begun carrying portable transceivers under their jackets. These transceivers send out signals that can be picked up from a distance of a few dozen meters by rescuers carrying the same device. But the best detection device around is the dog's nose. Properly trained, avalanche rescue dogs can cover in 1 hour as much terrain as 20 seasoned rescuers. These dogs learn to distinguish the scent of bodies trapped under snow from that of the rescuers around them. They have no trouble doing this, even when the victims are buried under 2 or 3 meters of snow. In spite of everything, avalanches continue to take a mounting toll. Scientists believe that toll might be reduced by better evaluating the risk of avalanches in a given area. It is possible to simulate an avalanche using a model of the area under study, submersed in a basin of water. Snow slides are studied by means of fine particles of heavy salt. This technique helps scientists understand how the velocity, direction, and mass of an avalanche is affected by the slope, the shape of the terrain, and the amount of accumulated snow. Studies are also being conducted with computer models that can simulate the slide of snow masses. They also make it possible to assess the effectiveness of protective shields against avalanches, which will slow down or detour snow slides. The computer can help determine the best location and types of structures to be erected as shields. Researchers are also attempting to refine their techniques for forecasting avalanches. As it now stands, these forecasts, broadcast every 24 hours, are largely based on the latest weather conditions. However, during the winter, snow surfaces change constantly. These internal changes can make some of the upper layers of snow wetter and heavier, and therefore more likely to cause an avalanche. Observations like these have helped the experts to devise an avalanche forecasting system. Based on daily weather conditions, the computer creates a detailed portrait of the snowpack, including its thickness, compactness, temperature, and water content of the various layers. That portrait enables them to monitor snow conditions in the various mountain areas and to assess the risk of avalanches all season long. Ultimately, scientists may well learn how to appease the wrath of the white goddess, the avalanche. The pleasure of taking risks? Adventure? Daredevil thrills? A famous alpinist, Mallory, was once asked why he climbed mountains. His answer was simply, because they're there.